Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this homework problem, you are asked to provide the product for the following reactions. We'll examine each reaction one at a time, and we will show how you can determine the product. So I'm going to give you a little more than you actually had to write down. In the first reaction, A, you were given the molecule cyclooctene. And just so you can, actually, more space there. Make sure there are 8 carbons. I'll put dots because when we shrink this, it may not be visible. Those are the carbon atoms. Okay. So we've got cyclooctene, and we're going to hit this with H2SO4 and water. Now the reaction with H2SO4 and water is an equilibrium reaction, and as a result the yields are not great. However, we follow Markovnikov addition with the electrophile attacking and protonating the double bond. We must always draw the carbocation that we would get. So I will draw that. H would add here. And actually, if you look at it, Markovnikov addition says the electrophile adds to a carbon with most hydrogens. Well, there's the same number of hydrogens, so it doesn't matter where it adds. So I will add the extra H here. This gives me a carbocation. I must always examine the carbocation looking for shifting. In this case, the carbocation is secondary. It's a secondary carbocation. No matter where I shift it, I will end up with a secondary carbocation, so the shift does not occur. That means the nucleophile will now attack. Now, if it was just H2SO4, you would possibly get the inorganic ester, the cyclooctyl hydrogen sulfate. But because of the presence of water and the fact that HSO4 minus is such a good leaving group, you actually end up forming the protonated alcohol, which then loses a proton, and it gives you the alcohol. Now, it doesn't matter which side you put the OH on. It is the same thing. But you'll get this alcohol. And the yields are not great. B. B is a little trickier because I gave you a cyclic alkyne. The smallest cyclic alkyne that could be made was Cyclononyne. The original question had cyclooctane, but I changed it to nonyne since that couldn't exist. So I'm going to make the diagram a little larger. So, hard to see where the carbons are, so I'll put dots for where the carbons are. Nice if that was a straighter bond. Count your dots. How many have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is a triple bond. Reagent I gave you was H2SO4 and H2O. Now for this course, this reaction will go whether or not I add mercuric sulfate to help catalyze and drive the reaction. Mercuric sulfate is a salt that's often added to this reaction, but I did indicate that the reaction will go with or without the mercuric sulfate. So we could put it in or we can leave it out. In this question, I chose to leave it out. So don't be surprised if you don't see mercuric sulfate. Again, we get Markovnikov addition, H+, there's no shifting, OH will attack, and the species I would get. Oh, let's try this a little higher. So carbon, 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 carbon. Okay, and what we would do is we'd keep one pi bond. To one of the pi bonds, we'd add an extra H. That would make a positive where the OH would attack. I'd get something like this. Now, this is an intermediate enol. We learned that enols are unstable and tautomerize to the keto form. Essentially, this H will shift over to here. The pi electrons will grab the H, and the bond will create a double bond. And so what we will get as a product my carbons, and I will get a double bond O, the keto form. The enol tautomerizes to the keto form. Right? How does that happen? If you are confused, well, look at it this way. I can draw a resonance contributor for this guy, where a lone pair dumps in and creates a pi bond here, and this moves over here. So this resonance contributor helps explain how this can happen. So I'll get a minus here with an H. I'll get a double bond O, H, positive. And here are my carbons, just so you can see them clearly. That's a lone pair, so that's a lone pair there, so this lone pair dumps in. Now what we've got charge separation on this, so this is a minor contributor, but you can see how if I lose this proton and place the proton where the lone pair negative charge is, I'll get the two H's here, and I'll have a ketone. So while the enol has a resonance contributor that looks like this, these two are tautomers. Now tautomers, remember, are defined as where you move either lone pairs or pi electrons and one or more protons. And because you're shifting atoms, tautomerization is not resonance, it's an equilibrium. So these two molecules are in equilibrium. This is the enol's resonance structure, which is very similar to the keto form. This is the product, however. You must remember to convert the enol to the keto form. Okay? Let's try question C, because question C was tricky. In question C, you were given this molecule. It's reacted with H2SO4 and H2O. So again, we have to watch for rearrangement. The acid will protonate the double bond to generate a carbocation. We look for Markovnikov addition. Markovnikov addition would state that the electrophile will add to the carbon with the most hydrogens. In this case, there are the same number of hydrogens off the double bond. So the first thing that jumps into your mind is, hey, it doesn't matter. That is, I could get Markovnikov addition this way. Where the H adds here. And that would give me this guy. Or I could add Markovnikov addition to the other one because it's had the same number of hydrogens. So I would draw these carbocations on scrap paper and look closely at them. For example, I might notice that, hey, this guy right here is a secondary carbocation. So I could do a shift this hydrogen over, a 1-2 hydrogen shift. You have to watch for rearrangements. If I do that 1-2 hydrogen shift, my secondary carbocation comes CH2 here. And I get a tertiary carbocation. Now, the question you have to remember is what causes Markovnikov addition? Why does the electrophile add to the carbon that gives you the most hydrogens? And the answer to that is when the electrophile adds to the carbon with the most hydrogens, you usually get the most stable carbocation. That's why it works. So Markovnikov addition isn't the only thing that controls, isn't what really controls the direction of the electrophilic attack. It's actually the stability of the carbocation. So one has to ask themselves, will this carbocation, let's label them A, or carbocation B form? Initially you might say, A and B are both secondary carbocations, so B, because it can shift to a more stable one, would be favored. But in actual fact, if you say that, you're forgetting something. Carbocation A is resonance stabilized. Carbocation A is resonance stabilized. And because carbocation A is resonance stabilized, it is more stable than carbocation B. Energetically, it is lower energy, and therefore it is favored. Now, because it is favored, and energetically lower energy, carbocation A will form in preference to B. B will not form. Now, if that's the case, because it's resonance stabilized, there's no shifting, carbocation A forms, then what I'm going to get having a little mouse problem here. seems to be working better now. So I can draw the product now. And this would be the only product because it is the most stable carbocation. So sometimes you follow Markovnikov addition rules and it doesn't reveal the most stable carbocation. Don't forget about your normal carbocation stability rules. Okay, let's try question D. In this case, you were given 2-methyl, 1-propene, or just 2-methylpropene. And you were asked to react it with 1BH3 and 2 peroxide in base. Now, this is called hydroboration oxidation. It is a mechanism that produces alcohol in high yields. It gives you no rearrangement, and it goes anti-Markovnikov. Now, in actual fact, the boron adds in a Markovnikov fashion, producing a trialkyl borane. But the completed product looks like H plus added anti-Markovnikov, so it's referred to as having undergone anti-Markovnikov addition. In that case, since there is no rearrangement, high yields, anti-Markovnikov product, that means the hydrogen, when it produces the alcohol, the electrophile, adds to carbon with the least hydrogens. Well, that's this guy. And that means the OH will add to the carbon who had the most hydrogens. And so this is my product. Question E is an interesting one. We're given this alkene. And this is good because it raises a question that I alluded to in question C, which we can discuss here quite nicely. So this alkene, H2SO4, and water. Now again, we look for Markovnikov addition, but we see up this alkene there's the same number of H's. Well, maybe this is a trick question. Could there be some resonance stabilization? Well, in actual fact, the answer is no. If I add the H here, I'll get this carbocation. If I add the H here, I'll get this carbocation. Now what's interesting about this carbocation is this carbocation will undergo a 1,2 hydrogen shift because he's secondary. There's no resonance stabilization, so the H that is here, that H, will shift, and you will get this carbocation. In other words, the hydrogen will shift here and put the positive charge at the methyl. That's awfully small. I'm going to try making it a little bigger. So plus is here. We now have a tertiary. So we go from a secondary carbocation to a tertiary. Now here's the question. And I made the same erroneous statement in question C. This time there's no resonance stabilization favoring this guy. This is a secondary carbocation. That's a secondary. The formation will occur equally. However, in this case, the 1,2 shift produces a tertiary. Does the fact that the tertiary is more stable and that the shift can occur prevent formation of this carbocation? And the answer is no. Initially, before the shift, there's no energy difference, and that means both are going to form approximately 50-50. But this guy will 1,2 shift, so you'll never get the alcohol in this position. So that means there will be two products. You will either get the OH attacking the carbocation in this position, or you will get the OH attaching to the shifted position in the other carbocation, because the shift happens faster. So you get these two. Is one major or minor? We cannot tell in this case. And the answer is no. Now what would happen if we had used as our reagent in question F, we're given mercuric acetate and water followed by sodium borohydride and H2O. The difference here is the mercury. Mercury is the electrophile. Now, if mercury adds here in the first step, it's a large atom and it helps stabilize the carbocation. If mercury adds here, again, it is a large atom and it has an acetate attached to it. And because of this, mercury stabilizes the carbocation, preventing the shift. So mercuric acetate will still give you Markovnikov addition, but it will prevent the shift. So you don't have to worry about shifting. So if I draw an arrow now where I go water with mercuric acetate, O2CCH3 twice, and then 2 sodium borohydride, H2O, and hydroxide. The exact same products form, except you don't get the shift. So because there's no difference in stability, attack can occur equally at either side. But this time, there is no shifted product, because mercuric acetate prevents shifting, stabilizes the secondary carbocation, so the OH will go on either side. Now, we have no extra stabilization of either carbocation. Markovnikov addition follows. You add to the carbon with the most hydrogens. In this case, both carbons of the double bond have the same number of hydrogens. You get random attack at either end. You'll get both alcohols forming. Well, there you have it. That is the homework dealing with hydration of alkenes with H2SO4 and H2O, oxymercuration, demercuration, which produces alcohol, and hydroboration oxidation, which also produces alcohol. I'm Dr. Brian Lloyd. This is my Scribblecast. Thank you very much.